Hi everybody. We're starting the second week with right triangles. Last week we looked at geometric means and the Pythagorean Theorem, and I just want to warm up today, give you an assignment too, about the Pythagorean Theorem with a few solids. First I want to talk about how we could use the Pythagorean Theorem if we're studying a cube. When I say solids, just three-dimensional figures, and we'll talk about a cube, and that's a kind of a nice thing I have. I got a thing called the geometer, and it helps you to draw things. But I think you could draw them also. And let me just show a cube here. And all you got to do with your ruler is draw a square just like I did. It may not be nice as this one. But then once you draw that first square, I'm going to scoot over a little bit, maybe over just a little bit like that, and draw another square. Which I tell you I could do with just my ruler. And then I'm going to connect these corners. And I'll have a pretty good looking cube here in a minute. I won't make you watch me draw all these figures, but I just want to get started with you making some sketches too. So I'm going to say I have a cube, and the upper plane could have been A, B, C, D, just so we can talk about it. And you should sketch one too, please. A, B, C, D. If I'm in class, I'll turn this off for a little while, and everybody can get a chance to sketch it too. D, Q, R, S. And we're going to talk about diagonals. Face diagonals, a face diagonal. Each of these are faces. I like to kind of shade the bottom face, the base of it. It kind of helps people to adjust to looking at the cube, because everybody looks at it a little bit differently. But let's say that each edge on this thing has a length, well, we could say 10. Each edge is 10 centimeters. And I want to know a couple of things. I would like to know about a face diagonal. How big is a face diagonal? And then the length of the main diagonal. Let's do a face diagonal. And that's a pretty simple thought. And you would be thinking, well, all the faces on this thing are square. And if each edge is 10, like the distance across here is 10, it's 10 tall, 10 deep, 10 in all directions, probably has a volume of about 1,000, but that's not what we're here to talk about. I'm going to just draw a square on the side. And I'm going to find the length of a diagonal in that square. And that'll be where the face diagonal would be, because all the faces are squares and we just want a diagonal in one of the faces. And if this is 10 and this is 10, and even though we don't know a lot about special right triangles yet, I still think we could find the length of that diagonal, which is like the diagonal across here, huh? Yeah, let me draw it that way, across AC. But the truth is, all of the faces are squares that are congruent to this one, and all of the face diagonals would have that same length. And you might know that length already. I'm going to call it D. I'm going to call it X. I already got a D over here, I imagine. So, wouldn't it have to be 10 squared plus 10 squared, as we hit it with the Pythagorean Theorem, equals D squared? And it'd be good if you knew the answer to this already, but you know that would have meant you're really paying attention to a lot of other things. That's 100. Plus another 100 is equal to the diagonal square. That's 200, isn't it? Is equal to the diagonal squared, and we're going to take the square root of both sides. And that is 100 times 2, clearly. And we'll reduce that radical and call it 10 times the square root of 2. That's what x would have been here. And that's the length of a face diagonal. And I hope you're recognizing that any other cube in the world would be similar to this one. Sides in the same ratio, diagonals in the same ratio. But now what about a main diagonal? A main diagonal, this thing has lots of main diagonals. That's one from every vertex in the upper. So we have 4 different main diagonals. But a main diagonal goes through the solid, through the center of the solid. I can show a picture of a main diagonal if I went from C to P. I'm going to show that. That would be a main diagonal. And we need to find its length. And it does exist in a right triangle. Maybe you can see the one I'm thinking about. I'm going to shade a right triangle right here. I know it has a right angle here. And I think we just found this length right here, AC. That was 10 square roots of 2. I think this edge is just 10. And the main diagonal, PC, that's the hypotenuse on a right triangle with those two sides. I'm going to go for the length of the main diagonal now. Let me make that note. And in a minute, I'm going to shut this thing down and you'll have to do a cube and a rectangular solid and a pyramid, just like we're going to do right now. But let me get the main diagonal for this fellow. And I would hit it with a Pythagorean theorem, and every cube's going to work a lot like this one. It would be 10 squared plus 10 square roots of 2 squared is equal to, I want to call it, I guess, MD for main diagonal squared. Square, and that's easy, that's 100. But now, how do you square this fella? I guess we'll be talking a lot about that. Let me do it on the side. If it was 10 square roots of 2 squared, that's really 10 square roots of 2 times 10 square roots of 2. And when you multiply numbers with radicals, you multiply the outside with the outside. That'd be 100. And the inside guy with the inside guy, that'd be the square root of 4. And since the square root of 4 is just 2, we're going to multiply 2 times 100, and this has got to be 200. But I can see how that's going to, so that answer is going to be 200. But we can think about this, and we'll have to go through all of that. When you square a number with a radical, you square both parts. The square of 10 is just 100. And a clever thing for you to know, that the square root of 2 squared is just 2. The square root and the 2 and the squaring are inverse operations. They undo each other. The square root of 2 squared is just 2, so that's 100 times 2. And that's 200. And maybe you knew that already, and I'm glad. So we do know that when I square this amount right there, I get 200. I'm using the Pythagorean theorem. Is equal to the main diagonal squared. I got to add those up. I got 300, huh? Is equal to the main diagonal squared. Take the square root of both sides. Square root of the main diagonal squared, that's going to be that main diagonal. But now what about the square root of 300? Well, it is 100 times 3. As we seek to take out perfect squares, I know the square root of 100, and that would be 10. I do not know the square root of 3. It's about 1.734, but no, that's not what we want to talk about. So we're going to leave the square root of 3 inside the radical. So, and I would say that the main diagonal is 10 square roots of 3. In class, we may practice another one like that, but for sale, kids, I'm not going to do it 2 or 3 times in front of you. If you ask me to, we'd work another one, but I would say that all cubes are going to be similar to this one. So at the end of this thing, I'll ask you to make a cube that is 8 inches on the side, or 8 centimeters on the side. Give the length of all the face diagonals and all the main diagonals. But I'll remind you about that at the end. Next thing we're going to look at is a rectangular solid. It's a lot like a cube, but it's not as predictable. And if I was going to draw a rectangular solid, I'm going to do that in front of you. And you don't have to go get a geometer, that's not the deal. But you just got to use a ruler, draw a rectangle carefully, and then draw a congruent rectangle that's just a little bit moved over. I bet you lots of you are better artists than I am. I know that's true. But I'm the guy that's doing this right now, and I just want everybody to be able to do this. Connect up these vertices, and we have a nice looking rectangle. I'll give us some links, and we'll figure out some diagonals as well. You know, you don't have to have that geometer. It wouldn't have been a bad thing to just draw a rectangle as carefully as I could. Draw another rectangle like it, moved over a little bit. And this won't be very well done, but it'll work for our processes here. Okay, bring that a little bit further. And we're going to get a rectangular solid, like a shoebox. And let's find some face diagonals and main diagonals. We'll probably need to name the vertices. Other thing that is helpful to me also is if you shade the bottom base, it kind of makes it easier to adjust to. I'm going to call the upper base A, B, C, D. We might just do this every time just to keep it simple. A, B, C, D. And then the lower base P, Q, R, S. And let me give you some links. Let's say that this rectangular solid is 9 inches by 12 inches by 20 inches. And it really doesn't matter to me where you put those, but we'll say length, width, and height. No. Let's let the length be this one. No, it's more obvious that we go that way. So let's that guy be 20. And these could be 9 by 12 either way. Just rotate the guy and it won't make a difference. But I'll make this one be 12 tall and that edge across the base right there, let it be 9. You would recognize, I hope, that the bottom base and the top base are congruent. They don't look so in this picture so well, but they should be, if this is a rectangular solid. The left face and the right face are congruent. The front face, DCRS, is congruent to the back face, ABQP. So when I work with this rectangle on the right, I'm also thinking about this rectangle on the left. I'm going to go for the length of diagonal CQ. That's a face diagonal. I'm going to find the length. We're going to find the length of all 3 face diagonals. Let's go with CQ first. CQ is the hypotenuse of a right triangle there. I got a right angle right here at R. And this length would have to be 12 if DS was 12. So I'm going to use 12 in that Pythagorean theorem. I'll go ahead and write it on the triangle, why not? And this length across the bottom edge is the same as this length. That's just a rectangle on opposite sides of a rectangle, so this length has to be 9. And we'll hit that right triangle with the Pythagorean theorem. 9 squared plus 12 squared equals CQ squared. And if you knew about Pythagorean triples, you might can predict this one. In class we can talk about that, but 9 squared is going to give me 81. 12 squared is going to give me 144. It's equal to CQ squared. And these add up to 225. We'll take the square root of both sides, and you might recognize that's to be 15. CQ is 15. This length would have had to be. Let's get other diagonals. Let's get a face diagonal. How about for this upper face? And you can name either way you want to. I'm going to call it DB. And rather than trash this figure, I'm going to draw a new rectangle, just like that upper face. ABCD. And do a face diagonal there. I'll get the length of diagonal BD. I know that this length was 20 because SR was 20, and therefore AB and DC would have been 20. And I know that this edge, AD, is congruent to this edge, SP, so it would have also been 9. I got a right angle here. I'm going for that diagonal face diagonal DB. And I'm going to hit it with the Pythagorean theorem. I don't think it's going to be too pretty, but we'll see what the square root of 481 looks like. Let's see. 20 squared plus 9 squared ought to equal DB squared. So 481 equals DB squared. So DB equals, I can't do much with the square root of 481. We just have to leave it like that. But that's what DB would have been. Is there another face diagonal we could figure out about? I got the one on the top base, DB. I've got this one on this side. How about on that front face? There's another rectangle that is the front of this thing. I'm going to sketch it right here, right now. That could have been diagonal face DCRS. And I'm going to find the length of that diagonal. I'll call it CS and go for it. I got to know these sides. SR, yeah, that was 20. And you could work from this figure, but when we do the main diagram, I want to use this figure to illustrate. And this vertical part here, I am doing a front face, aren't I? Yeah, that's CR. That vertical thing's 12, isn't it? And I have to hit that with the Pythagorean theorem, so let's see what 544 will do. But I believe that'll be kind of more interesting. We'll see. 4 will go into it anyway. 20 squared plus 12 squared is equal to SR squared. I got 400 and 144 equals SR squared. We got to figure out about the square root of 544. Alexa, how many times does 4 we're going to 544? It must be
544 divided by 4 is 136.
Oh, we like 136. 136 times 4. Alexa, how many times does 4 go into 136?
136 divided by 4 is 34.
Ah, so this is 34. times 4 times 4. That's 34 times 16, huh? Hey, Alexa, what's 34 times 16?
34 times 16 is 544.
Let's bust that radical down. That's kind of a nice one. We can get the length of diagonal CS. It's the square root of 544, and Alexa tells us that's 16 times 34. So CS, you would tell me, is 4 square roots of 34. And those are all good, just a nice use of the Pythagorean theorem. I wish I would have done a cleaner job. But there's one more thing we got to look at here, and that would be a main diagonal. You remember the main diagonal on that cube? The main diagonal on the cube went through the solid. And actually, all the main diagonals would have the same length on a cube. Truly, all the main diagonals on a rectangular solid would also be the same length. Think of about like a shoebox, and these distances would be the same. We found the length of diagonal CQ. Which segments would be the same as CQ? BR would be, but also the diagonals of the opposite square, AS and DP. I just want you to recognize when you find that one diagonal, you really found 4. And when we found that diagonal DB across the top, that's the same as AC and as PR and SQ would have been. So those opposite faces are congruent, and their diagonals would be congruent, and the diagonals of a rectangle are congruent. If I measured this diagonal, it's the same as that I measured that one. We'd be using the same numbers as we use the Pythagorean theorem. But let's go for that main diagonal. And I could do that a couple of ways. Let me just sketch a main diagonal here. And I hesitate to use it, but I'm going to use BS. And we're going to find the length of BS. That is a main diagonal. Although, CP would have worked and AR would have worked, but I think I could show this triangle a little bit better. I'm going to show the right triangle that holds BS as its hypotenuse. I'm just got to darken it so you can see what I'm talking about. BS is the hypotenuse of a right triangle. And I think we know some sides on that right triangle. The right angle right there. Hit this with the Pythagorean theorem. We're going to find BS, the main diagonal. That's really the big deal here. I took a little time to write main diagonal BS, and I'm talking about this figure. But if I went around here, maybe that would be a good idea. A, B, C, D. And that's PQRS. And he's going for BS. Yeah, he is. And he thinks it lives in this right triangle right there. As the hypotenuse of an angle there, of a triangle there. We would have to know this length, and we do know that length. That length was 12 on this figure. That's the vertical height. And we would have to know that face diagonal right there. And that face diagonal is the same as SQ. And didn't we find SQ? What we get for SQ? DB is the same as SQ, isn't it? DB being the diagonal of the upper rectangle. SQ is the same as that. So when I'm hitting with that length SQ, we should have been same as DB, the square root of 481. Looks kind of dreadful. But let's hit that with the Pythagorean theorem. I think it's going to come up kind of pretty. Let's see how that goes. Looking for that hypotenuse, BS. Square root of 481 squared plus 12 squared ought to equal SB this time squared. And that's got to be 481 when I square it. And when I square 144, that's got to be, when I square 12, I got 144. Hey, Alexa, what's 481 plus 144?
481 plus 144 is 625.
625. Hey, that's a real nice number. I know the square root of 625. Alexa, it's 25. What's the square root of 625?
The square root of 625 is 25.
That's the length of our main diagonal. It would have been 25. We could have done that very differently. I think I want to take you down that walk, but we'll do that in class. I would just tell you, I don't want to make this video any longer than it needs to be. You can hit it with this triangle just as well. Maybe I should do that right this second. I'm going to. With a right angle right here, we're going to get the same length for that main diagonal. And I think it'll probably go a little quicker this time. Doesn't that look like it's got the main diagonal as a hypotenuse? Do we know that face diagonal AS? I believe that we do. CQ was 15. AS would also be 15. So I'm going to go 15 squared plus. And this length we knew, that was 20, wasn't it? Plus 20 squared is equal to the main diagonal SB squared. I could have used other ways to approach this. And this is pretty numbers, huh? That's 225 plus 400 is equal to SB squared. Just finding that main diagonal again. I sure do get 625 again, huh? Is equal to SB squared. And when I take the square root of both sides, we recognize that square root of 625 is just 25. And there might be somebody out here who recognizes this as it was 15, 20, and 25. Yep, 25 for that one. That's just a big 3, 4, 5 triangle right there, huh? We're talking about Pythagorean triples in class, and this is a 3, 4, 5 triangle. That's why I wrote this question in the first place. That's a good kind of question for you to work with, finding face diagonals and the main diagonals there. We'd also like to look at a square-based pyramid. I'm going to sketch one. We'll talk about it. When I got to draw a square-based pyramid, I start by drawing a parallelogram, because that base in perspective would look like a parallelogram. I go around thinking, I'm going to call that base, and it's supposed to be a square, A, B, C, D, but it does look like a parallelogram. And I think to myself, where the diagonals would intersect, I think that's the center of that polygon, and directly above that, I'm going to make that be the vertex of my pyramid. I'm going to call it V, and I'll often do that. And I'll just connect it to the vertices of the base, that is. And it'll be a pretty good looking square base pyramid. Not great, but it's workable. You've got to draw a few of them, and I don't really like that one very much. This face is kind of hard to see. So let me look at another one. And I just start with a couple of parallel lines and make a parallelogram, which will represent my square base. Choose a place right above the center of the base where I think the diagonals would intersect. And go to where I think would be a nice place for a vertex, and then I'm going to connect those up. I'm not saying that you couldn't draw a better pyramid than me way before you ever met me. I'm just saying if you didn't know how, here's a way you could. And I want everybody to be able to draw a pretty good looking pyramid. And I'm happy with this one. I think we'll work with this guy. Let me give you some lengths, and we're going to figure out the length of a slant height. The slant height goes from a vertex of a pyramid to the midpoint of an edge, of a base edge. I didn't draw that one as well as I want, but we're going to accept that that's a midpoint right there. That's a slant height. And when I give you some links here, we're going to figure out slant height and the altitude of the pyramid. The altitude of the pyramid would be from its vertex to the center of its base. I'm going to show that one too, just so you'll be thinking about it. We're going to find that length and this length. I'll give you the edges and the base edges. And it's a square base. Let me write that out and do a couple of things here. Let's say that each edge on this pyramid is 12. This is 12 on an edge. And these lateral edges are also 12. So every edge you could touch, VA, VB, everything's 12 on this guy. So I would like to find the length of the slant height. Let me make a little note that that is a slant height. On your sketch, you ought to as well. GHT. It goes from the vertex to the midpoint. And just so we can make it clear, let's call that M, being the midpoint of that segment right there. And first thing I want to find out is the length of VM. It lives in this equilateral triangle. If each edge is 12, then that's an equilateral triangle. I'm going to pull it off and get a good look at it. There it is right there. That's triangle VAB. And I wish I knew the length from V to M. Finding that length right there. And it's going to go kind of smoothly. This length would be perpendicular to that base edge. There's a right angle here. These sides are all 12. You might recognize that the altitude in an isosceles triangle or an equilateral triangle is going to bisect the base, so this would have been 6, and so would that. But what I'm caring about is that length right there that I labeled as Z. And we get hit with the Pythagorean Theorem, and it's quite a predictable thing. Let's see what comes there. 6 squared plus Z squared, because 12 is the hypotenuse, is equal to 12 squared. And we got 36 plus z squared equals 144. Subtract 36 from both sides, we got z squared is equal to about 108. Take the square root of both sides. Now, this is sort of interesting. 144 is 36 times 4. We took out one of those 36s, as a matter of fact. So now they've got 3 36s left, huh? That's 36 times 3 is equal to the square root of z squared, which is just z. So we would report now that z is 6 times the square root of 3. That's what that length would have been for the slant height. Label it that way, because I want you guys to label stuff when you turn it into me too. The slant height is 6 square roots of 3. Let's go for, I'm going to call that center of the base x. Let's go for the altitude. Altitude Vx. And it lives in a right triangle as well. The altitude is by definition perpendicular to the base. Therefore perpendicular to any line in the base that passes through its foot. It would be perpendicular to mx, wouldn't it? And I think we have the power to know the sides of that right triangle, so we could come up with Vx. Vx is not the hypotenuse, but that's okay. We do know the slant height, don't we? In this figure, it was 6 square roots of 3. And we know that this full length across the base edge is 12. This is, in fact, the center of the base. So if I went from M all the way across there, it'd be 12, wouldn't it? So to the midpoint there, to the center, it would have been 6. Let's hit it with the Pythagorean Theorem, figure out about Vx, huh? And you'll say, well, let's be a little bit careful because the slant height is the hypotenuse, and that's 6 square roots of 3. So this would look like 6 squared plus Vx squared is equal to 6 root 3 squared. Nice way to work with these numbers, isn't it? Very, very predictable, but you haven't seen very much of these yet. This is 36, isn't it? Plus Vx squared. Then what you got there? Well, I got 3 36s when I square this. I get a 36. When I square that, I got a 3. So this is 36 times 3. 36 times 3, which is really 108. But, go back to this equation. 36 plus Vx squared is equal to 108. Let's subtract 36 from both sides, and I got Vx squared is equal to 72. Take the square root of both sides, and Vx would be, and as we take the square root of 72, since that's 36 times 2, isn't it? And keep taking those 36s out, I get 6 root 2. That would be the length of the altitude in this square base pyramid with all the edges of length 12. Now, let's agree on what you should do. First off, I want you to make sketches. All right? That'll be first jump. You got to show the sketches. I'll tell you what, I'll list those things and come right back and talk to you about it. Okay, here's pretty much what I want you to do for an assignment. I just scribbled it right here, but I want you to make sketches every time. You're going to do 3 solids. You're going to show me a cube. And with that cube, you want to make a statement about it. Show me the Pythagorean Theorem every time, even though you already know what the answer is going to be. Demonstrate the Pythagorean Theorem as you find a face diagonal and a main diagonal. Let's say that each edge on the cube is 8 inches. So you draw a cube. Boom, boom. A lot better than this one because you'll use the ruler and do it well. You'll draw a quick cube, make each edge be 8, and find a face diagonal and a main diagonal. You'll probably talk about right triangles in there, or think about right triangles that would make that happen. You'll also do a rectangular solid. And I'm just scribbling right now. You won't just scribble when you do yours. You'll show something that looks sort of like this. And the dimensions I want to put on there, let's say, are 6 by 8 by 24. That's not x, that's just 6 by 8 by 24. And you can make this be 6, and this would be 8, and this would be 24, and that'd be great. And I want you to find 3 face diagonals, like you'd want that face diagonal. Probably across the front, a face diagonal, and one for the top edge, top base, a face diagonal. So you can find those. And then you also want to get a main diagonal. The main diagonal for this guy, my sketch is looking a little bit wild right now, would go from, for example, this vertex to that vertex. That would be a main diagonal. And I believe this is going to be the hypotenuse of a right triangle. I can tell which one right there. But you'll make a better sketch than mine and find your own hypotenuse and work that out. I want you to figure out the main diagonal in your rectangular solid that is 6 by 8 by 24. And this is a little bit different. I want you to do a square-based pyramid. And the last one we did where all the faces, all the edges were the same. And I'm saying this time, let each base edge be 10. The base is a square, 10 by 10. You might want to draw that square on the side just so you can be thinking about things. This is 10 and this is 10. That's that base, but each lateral edge is 13. If this were the vertex and these are the edges of the base, A, B, C, D. A lateral edge would be like VA or VB, VC or VD, and they're all congruent. These are all going to be isosceles triangles. So let's say the lateral edges are 13. And what are you supposed to do? Find a base. Given that base edge, you got to find the slant height. The slant height goes from a vertex to a midpoint of a base edge. And see, that's going to work with a right triangle, and that's a midpoint, so you can get that length, and you know the hypotenuse. That'll be easy. And then you've got to find the altitude as well. The slant height and the altitude is what you got to do here. You drop that altitude, looking about like that. Hit it this way, and you can hit it with that Pythagorean theorem. You know the hypotenuse already. It was the slant height. You know that's 1/2 the distance across the bottom of the pyramid. So you can figure that and hit it with the Pythagorean theorem. And if you wanted to be kind of wild, you could show this segment and look at a different right triangle. But it doesn't matter to me which right triangle you use, but I think that one would also work. We'll probably do that one in class, and so that it have the same amount as you show part of a diagonal for that base edge. How long would that segment have to be from the center to that corner? I'm not going to talk about it right now, but this is your assignment. Draw a cube and give me the length of a face diagonal and the main diagonal. Draw a rectangular solid 6 by 8 by 24. Give me the 3 face diagonals and the main diagonal. Draw a square-based pyramid with each base edge being 10 and the lateral edges being 13. Centimeters is fine, or inches is fine, I don't mind. Inches is great. Find the length of the slant height and the altitude. That's a great assignment. Let's be the next thing we do.